Hi guys, let's talk about normal distributions and z-scores. Normal distributions and z-scores. So first off, let's talk about what it means to be normally distributed, some calculations with normal distributions, and then we will discuss just a quick example and kind of preview where we can go next with this. So, what does it mean to be normally distributed? So everything I'm about to talk about can't happen unless things are normally distributed. So when you read these problems, typically there's going to be some sort of mention about things being approximately normally distributed. Okay, if not, could you technically do them? Yes, but it helps to have that added bit, which I'm now glancing at my example. I didn't write that in there. I'll fix that when we get there. So what does it mean to be normally distributed? To be normally distributed, you need a distribution that is roughly symmetric and unimodal. So if you took all of the data you're working with, you look at it and you do some sort of graphical display, a stem and leaf plot, a box plot, histogram, something, you need to see that it is roughly symmetric and unimodal. Okay, with both of those things, that means your data set is approximately normally distributed. So you're going to end up with this nice bell curve. So a lot of people think, oh, to be normally distributed, you need to be bell curve. Well, what does that mean? That means you need roughly symmetric and unimodal. The center of this bell curve is going to be your population mean, and you're going to have one standard deviation out. So using this mean and this standard deviation are going to be extremely helpful here in the future. So once things are normally distributed, that allows you to do a standardized z-score, or you might just hear me commonly call them just z-scores. So in order to do a z-score, you're just going to take the observed value minus the expected value divided by the standard deviation. Observed minus expected divided by standard deviation, or in symbol form, x minus mu divided by sigma, which is whatever data point you're dealing with, subtract off the mean, which is the same as your expected, and divide by a standard deviation. So that's why standard deviations, which was my previous video, are incredibly important. So take your whatever data value you're working with, subtract off the mean, that's an expected, divide by the standard deviation. Those are your calculations for z-scores. So I'm going to talk a little bit about in this video what can we do with a z-score, and in the next video I'll talk about more things that we could accomplish with z-scores. So let's get it to our example here. So student A took an AP Stats test and scored a 74%, but the class average was a 71% with a standard deviation of 5.5%. Student B took an AP Bio test and scored an 82%, but the class average was a 79% with a standard deviation of 7%. Who did better and why? And I kind of ran out of room here on my paper, but what I would like to add to this problem, if I went back and rewrote it, is say the scores of the AP Stats test were approximately normally distributed. The scores of the AP Bio test were approximately normally distributed. When they're both normally distributed, that allows you to do z-scores. So a little bit lazy in my writing here to try and put together just a basic example, but that needs to be there to allow you to do z-scores. So let's just go ahead and talk about that, add that in, that things are approximately normally distributed. So what we can do with z-scores is, as long as things are normally distributed, a standardized z-score does exactly that. It standardizes it. So it forces your z-scores to be on a common number line here. So you have z-scores that are going to range up to a positive 1, 2, and 3. They can go higher, and then down to -1, -2, -3. So it's going to take two things that are hard to compare and put them on the same kind of level so you can easily compare and say, this one is better than that one. Because it's not super easy to say, was the AP Stat test easier? Was the AP Bio test easier? Who knows, okay? They're two different tests, two different topics. So what we do is we could do z-scores as long as things are approximately normal to actually put them on the same level. So what I can do is I can calculate a z-score for the stats test, and then I could calculate a z-score for the bio test, and then we'll compare those two numbers and see how did we do, okay? Because simply just looking at the stats test to say, well, student A scored a 74 and student B scored an 82, therefore student B is better. It's not that simple. You actually have to go a little bit further than that. There's more things that you should account for. Class averages are important. Standard deviations are important. So we're going to take all that into account with a z-score. So for the stat test, if I was going to do a z-score, remember it's my observed value minus my expected value divided by the standard deviation. The observed value was what I got. So student A got and scored a 74%, so I'm going to start with a 74. We just subtract off the mean, which is the average, and it says the class average was a 71, so 74 minus 71, and the standard deviation of 5.5, okay? So I'm going to do 74 minus 71 divided by 5.5. So really quickly, if we do that, you're going to get a z-score of 0.55, because 74 minus 71 is 3. 3 divided by 5.5 is 0.55 if you round it to 2 decimal places. So there's my stats z-score. Going to do the same exact idea with my bio test, calculate a z-score, and then compare the two. So bio test z-score, I need my observed, which is what student B got, which was an 82. The expected is the class average, which was a 79. And the standard deviation was 7. So we're going to take 82 minus 79, which is 3. 3 divided by 7 is 0.43. 0.43. I know I'm a little bit tight there with my picture as well. 0.43. So now that we have my two z-scores, we can actually, since we're on the same playing field now, we can compare them. So you just need to think about, in the context of the situation, what is better? Do you want a larger z-score or do you want a smaller z-score? You know, in the case of tests, yes, bigger is better, higher score is better, so we want a bigger z-score. But there's other situations out there that maybe you want a smaller z-score, and smaller z-scores are better, okay? So like if I was doing a problem about like the number of cancer cells in someone, unfortunately, smaller is better. The less cells in you, better off you are. Where if you have a high amount, it's pretty bad, okay? So it depends on the context of the situation. You need to pay attention to that. So since we're dealing with test scores, I want bigger is better. So looking at the two, I have a z-score of 0.55, a z-score of 0.43. Since the 0.55 is better, I can say the stats test was better off than the bios test, okay? I can say the stats test is better than the bio test. So what does this also mean? What does a z-score even mean, okay? So yes, we are calculating, we are putting on the z-score, standardized and all that. What it means in the interpretation of these scores is it's the number of standard deviations above the mean that you are. So student A is 0.55 standard deviations above the mean. Meanwhile, the bio test, student B is 0.43 standard deviations above the mean. So z-scores, yes, can help you interpret where you are. Bigger is better, smaller is better, whatever. But it also tells you how many standard deviations above or below the mean is. So if you know, average is the mean, the larger above you are, or how many standard deviations above, the more different you are from the mean, the better off you are is kind of the idea there. So again, this is 0.55 standard deviations above the mean. The bio test would have been 0.43 standard deviations above the mean. So that's a little bit of kind of what z-scores can do for you. There are some additional things which I'll get into my next video, but I just kind of want to preview it here really quick, is once you have a z-score, it does unlock proportions and all that. So we're going to talk about here in my next video, the proportions that relate to this. So we could find cutoff points and say, well, what percentage or proportion of data is below a data point? We can figure out that. We can go above a data point. I don't want to draw like crazy all of this. Or in between. So there are more things that we could do with z-scores. Look for that in my next video where I talk about normal distributions and sort of the applications we can do with that. So again, this was normal distributions and z-scores.